In this video, we're going to discuss a new functional group set. Now these aren't part of our naming conventions, but they are relevant due to the reactivity seen in sugars. So we're going to introduce these functional groups here and then elaborate them when we talk about cyclizations of sugars. Reactivity here is between an aldehyde and an alcohol. So my aldehydes generically are to a carbon, double bond oxygen, then to hydrogen, or a carbon, double bond oxygen, and that carbon has two different carbon groups coming off it. Or they could be the same, just two carbon groups. If I add an alcohol, let's say ethanol, what will happen is the alcohol can attack that carbon that has the double bond. In fact, let's color code these. That oxygen attacks that carbon. The net result is that the bond here, one of the two bonds of the double bond oxygen, gets pushed up. This happens down here. That oxygen attacks one of these bonds, it gets pushed up. Well, what you will end up with will look like this. This is a brief intermediate. What will happen is the hydrogen gets pulled off the oxygen, and eventually it gets moved through various transfer processes. Another hydrogen will show up here. And in the process, those charges balance out. What we've done, however, is we've turned an aldehyde's oxygen into an alcohol that's still attached to the carbon the aldehyde's oxygen was originally attached to. And we've taken our oxygen from our original alcohol and we've turned it into an ether. When this occurs, this is an hemiacetal. Similarly, this happens for the ketone. You end up with R to a carbon, the other R group. The oxygen is now a single bond instead of a double. The alcohol's oxygen is now an ether, and the hydrogen has moved off the original alcohol to the new oxygen that is the alcohol. This is a hemiacetal. The way to tell these, if you ever find a carbon that looks like it has an alcohol and an ether. And so I've got an alcohol here up above, and I've got an ether down below. They're sharing the same carbon. If you see an ether and an alcohol on the same carbon, you are either a hemiacetal or a hemiacetal. Well, they are hemi because they're not done. If you were to add another alcohol, we'll say methanol, and usually it's the same as the original alcohol, but just for visual purposes here. Well, this oxygen on this alcohol can still attack that carbon. What will happen over time, as this happens, eventually it will displace the OH that we've drawn on top. And so you will end up with a molecule that has the original carbon chain, but that carbon, instead of having a double bond to one oxygen, now has two separate ethers attached. And then that top oxygen has picked up hydrogens from the available, either the solvent around it or from these molecules. So we draw it here showing that it has picked up the hydrogens that used to be on those alcohols. This is a full acetal. Similarly with the ketone, if this happens, my carbon chain remains, but my double bond to oxygen has been replaced with two separate bonds to different oxygens that are ethers. This is a full ketal. And again, water is produced. These become very important for sugar chemistry, but since we don't really have a naming convention for them, they won't be part of our naming. Nonetheless, this reactivity is very important. Sugars have alcohols and aldehydes on them, and so they will react with themselves to cause these reactions. How can you tell an acetal or a ketal? Well, if you find a carbon, and attached to that carbon are two ethers. Two separate ethers come off of that carbon. They share that carbon. That is your clue that you are an acetal or a ketal. These can also be reversed. If you have an acetal or a ketal and you add water, so instead of just making that product, let's say we add it. Well, water can attack that carbon and shove off one of the alcohols. And so it can reverse itself. So not only can you form the acetal by driving off water from alcohols attacking, you can also break those alcohols back off, reforming the hemiacetal. And if you were to take that, well, the other alcohol will drift away, and it's possible for those electrons that are on that oxygen to actually go down and shove the other oxygen back off. So it is possible, just on its own, that your hemiacetal can revert and become your aldehyde again. This also happens with the ketal. It's the same idea. So you start with an aldehyde and you add one alcohol. This will form the hemiacetal. That can either go back to being an aldehyde, or if a second alcohol attacks, it can continue on all the way to being an acetal by driving off water. Same with the ketone. If an alcohol attacks the ketone, you become a hemiacetal. This is capable of going backwards, or if you add a second alcohol, going on to be a full ketal plus a water. So your full acetal or ketal can only reverse if they have water. Your hemi is able to reverse at will or go forward if it has another alcohol. And so a lot of times if you make one of these, you remove the water. You have something in there that consumes and removes water so that you can never go backwards. Once you've reached an acetal, you're stuck there if you don't have water to go backwards. But anywhere in the middle, if you're a hemiacetal, it goes back and forth both directions for a while. This is the hemi and the full acetal and ketal.